Sunspots are as familiar to astronomers as the planets and our moon. Up until the middle of the 19th century, they were just an astronomical curiosity. But now, some scientists think that sunspots are visible signs of a mysterious mechanism that spawned significant climate change in Earth's past. Their theories are based on the frequent correlation between sunspot numbers, as recorded by astronomers down the centuries, and climate records. Scientists are now discovering that solar variation affects our climate in complex and subtle ways.
The number of sunspots on the surface, the number of solar flares, the amount of ultraviolet light does have a measurable impact on Earth's climate.
The first record of sunspots dates back to 800 BC. Galileo was the first astronomer to study sunspots scientifically, famously drawing the position of the spots in his notebook. Astronomers' records show that between 1645 and 1714, the numbers were so low as to be almost absent. At the same time, Europe and North America was suffering a period of cooling known as the Little Ice Age, which lasted for around 500 years. But during the Little Ice Age, there was a shorter period of brutal cold, lasting for just over 70 years, known as the Maunder Minimum. One winter during the Little Ice Age, it was possible to walk all the way from Manhattan to Staten Island over the ice. And in London, the Thames froze over for months on end. Londoners even held ice fairs out on the river. The fact that part of this period of severe cold was matched by low sunspot numbers has intrigued scientists ever since. A leading expert on how solar radiance influences our climate, Judith Lean.
There's a lot of anecdotal evidence that connects the sun's variability and climate change through indirect indicators of the sun's brightness and also of the surface temperature. And it's a very controversial topic because to understand it properly, we really need long-term records of the brightness changes itself and of the climate change.
Scientists needed more data, and that was a challenge. Galileo's records are the earliest that give us a clear idea of how much activity was going on. But now scientists have records of sunspots going back over thousands of years. They learned the key was not to look at sunspots themselves, but rather at an astronomical phenomenon which at first glance appears unrelated: cosmic rays. Scientists believe that cosmic rays originate from sources all over the universe, such as massive exploding stars. Charged particles fly out at close to the speed of light. Space is full of cosmic rays. They bombard the Earth continually, and we can measure the intensity of this bombardment over time. Cosmic rays collide with molecules in the atmosphere to produce isotopes, such as carbon-14 in tree rings and beryllium-10 in ice deposits. Thousands of years later, scientists can unearth the hidden records of this bombardment by measuring levels of these isotopes.
We can use carbon-14 to trace the sun's activity cycle going back literally thousands of years. And that's really amazing.
Levels of carbon-14 and beryllium-10 are affected by the sun's magnetic field in space. The sun's magnetic field is vast. Normally it extends 8 billion miles into space. But when the sun is more magnetically active, it stretches to 10 billion miles. Because cosmic rays are charged particles, magnetic fields deflect them. The more magnetically active the sun is, the more cosmic rays are deflected, leaving fewer markers in ancient trees and ice cores. Magnetism has long been used to deflect charged particles on Earth, too. Cathode ray tubes in TV sets do so to create a picture. Oxfordshire, England. At the Rutherford Appleton Advanced Physics Laboratory, British professor Mike Lockwood demonstrates how easily magnetic fields deflect cosmic rays. A simple beam of electrons created in a laboratory behaves in the same way as cosmic rays upon hitting the sun's magnetic field. This glass case contains a green beam of electrons that are physically similar to cosmic rays. Lockwood will simulate the sun's magnetic field with two metal coils.
When I pass electric current through a coil, I generate a magnetic field. And so if I turn the current up, I increase the magnetic field inside the bulb, and I start to deflect the beam. And the more I turn the current up, the larger the magnetic field and the more the deflection.
Just like the experiment, when the sun is at its solar maximum every 11 years, the sun deflects more cosmic rays away from Earth. So the number of sunspots appears to be directly related to the amount of cosmic ray deflection. This all ties together with events during the Maunder minimum. The carbon-14 data from trees reveals that the cosmic ray flux increased during this period, which suggests the sun's magnetic field became less active and the spots almost vanished from the surface.
We had the Maunder minimum, where there were few sunspots and a higher than normal flux of cosmic rays. And we can find other examples like that, and we can find periods like recent times when the sun's solar activity has been unprecedentedly high and the cosmic rays have been low as a result.
Thanks to cosmic rays, we have a historical database by which to investigate the changes in our climate and weather systems.